This is lesson 5.7, Systems of Linear Inequalities. You should be on page 274. In this lesson, you will learn how to check a solution to a system of linear inequalities first. Then you will learn how to graph a system of linear inequalities. From there, you will learn how to write a system of linear inequalities by looking at a graph. And finally, we'll use these techniques above in order to solve real-life problems. Now, a system of linear inequalities is a set of two or more linear inequalities in the same variables. You know, a system means exactly what it did earlier in the chapter. It means we have two or more inequalities, but those inequalities must have the same variables. You can see an example of that here. We have two inequalities, and both the inequalities have the same variables, x and y. Now, a solution to a system of linear inequalities in two variables is an ordered pair that is a solution to each inequality in the system. So, to be a solution to this, I would need an ordered pair that makes both of these statements true. So let's talk about how we check to see if an ordered pair is a solution to a system of linear inequalities. It's really easy. Just take the ordered pair, plug it in, and see if it works. So for this example here, let's see if 3, 5 is a solution. If I plug 3 in for x and 5 in for y, do I get a true statement? And I get 5 less than 6. That's true. Let's plug in 3, 5 in the other inequality. Plug 3 in for x and 5 in for y, and I get 5 is greater than or equal to 3 plus 1. That's 5 greater than or equal to 4. That's true also. That means 3, 5 is a solution of this system. Let's try the part B. Let's see if negative 2, 0. Let's see if this point would be a solution. Okay, I'll plug in negative 2 for x and 0 for y. And when I do that, you can look it down here, they're doing that. I get the statement 0 is less than negative 4. Well, that's not true. That means that negative 2, 0 can't be a solution to the system because it's not making each inequality a true statement. So this is not a solution of the system. What I'd like you to do is pause the video real quick and go ahead and try numbers 1 and 2. See if these ordered pairs are solutions to this system. And in number 1, I have to plug in negative 1 wherever I see x and 5 wherever I see y. So let's put a 5 in here. Is 5 less than 5? That's not true. Well, then that means negative 1, 5 is not a solution to the system. Okay? Let's go to number 2. I got to plug in 1 for x and 4 for y. Let's try that. So the first inequality, I get 4 is greater than or equal to 3 plus 1. That's 4 greater than or equal to 4. That's true. 4 does equal 4. And let's go to the second inequality. I'll plug in a 1 for x and a 4 for y, and I'm getting 4 is greater than 1 minus 1. That's true. 4 is greater than 0. So this is a solution to this system. So number 1, not a solution. The ordered pair for number 2 is a solution. Let's talk about how we graph systems of linear inequalities. The graph of a system of linear inequalities is the graph of all of the solutions of the system. That's key here because the only way you can answer these questions is by graphing them. You cannot use elimination or substitution for the following reason. Elimination and substitution will give you the one ordered pair that's a solution. You notice these problems have infinitely many solutions. So the only way we can find the solution set is to graph these. Now to graph them, obviously we have to know slope-intercept form. You're going to graph each inequality in the same coordinate plane. You learned how to graph an inequality in the last lesson. So This is a review of lesson 5.6. We're going to graph two inequalities in the same plane. From there, we are going to find the intersection of the half planes that are solutions of the inequalities. This intersection is the graph. So in other words, if you look in the book, they do a nice job. They color code this to make this easy. Like when you look at this sample in the book, the graph of y equals 2x minus 1 they did in red, and the graph of y is less than x plus 2 they did in blue. Where you see purple, that's the intersection of the problem. That's the solution. So let me kind of just color this in. So any of these points here would be the solution to this sample, okay, where I have in blue. And you notice there's infinitely many correct answers here. You have to graph these. So let's actually look at how we graph them then. Again, slope-intercept form is really important here. So for this problem, y less than equal 3. Okay, so here's what I'm thinking in my mind. First of all, I have y equals 3, which is a horizontal line. I'm going to trace it here 3 units above the y-axis. And I want less than equal 3. So if I plug in the point 0, I get a true statement. I should be shading below this line. And then here, y greater than x plus 2. My y-intercept is 2, and my slope is 1. So y-intercept 2, slope 1. So you can see y-intercept 2 going up 1 over 1, and I'm drawing a dotted line because I do not have equals. Okay, let's try 0, 0 for this one. If I put a 0 in here and a 0 in here, I get a false statement. 0 greater than 2 is not true, so I should be shading here. So do you notice I'm shading below the horizontal line and above this diagonal? My solution set would be in here. Okay? So they say then, they put here one solution is negative 3, 1. Do you notice how negative 3, 1 is part of the shaded region? Here's another solution. What about negative 5, positive 2? That would definitely be part of the shaded region. Okay? It is possible that when you graph a system of linear inequalities, you could potentially get no solution. So it's important to be able to recognize that. So here would be an example problem. Graph the system of linear inequalities. So here, let me rewrite this in slope-intercept form. Y would be less than negative 2x minus 1. I'm just taking away 2x from each side. Okay, so my y-intercept's negative 1. My slope is down 2 over 1. And I have a dotted line. Now let me think about shading. If I plug in 0, 0, which is to the right of this dotted line, 0 here, 0 here, I get a false statement. 0 is not less than negative 1, which means I should be shading this way for that dotted line. Let me pick a different color pen. I'm going to pick red, not that it's wrong, just so it shows up nice, okay? Let's now graph this. So y would be greater than negative 2x plus 3. I'm rewriting this into slope-intercept form real quick. My y-intercept is 3, that's here. And my slope is negative 2, down 2 over 1, down 2 over 1, and I need a dotted line. Okay, let's do my shading now. I'm going to test 0, 0. If I put a 0 in here and I put a 0 in here, I get 0 greater than 3, and that's false also. So I'd have to be shading this way. Do you notice where I'm mentally shading? I'm just thinking this. I'm not actually doing it. I'm just thinking about my shading. Do you notice my shading is not overlapping? That means that this problem has no solution. There is no overlapping shading at all. There are no points in common for both of these. Why don't you try numbers 3 and 4? Graph these systems of linear inequalities and find the solution set. Okay, so for number 3, y is greater than equal negative x plus 4. Now negative x means negative 1x. My slope is negative 1. So y-intercept 4, Slope negative 1, which means down 1 over 1, and I drew that line. Now let me test 0, 0. If I plug in a 0 here and a 0 here, I get a false statement. I get 0 greater than equal 4. That's not true. So I should be shading above that. Okay? So I'm just making a little note. Okay, now for my second inequality, x plus y less than equals 0. I'm going to take away x from each side, so y is less than equal negative 1x. So this has a y-intercept of 0 and a slope of negative 1. So here's my y-intercept of 0. I'm drawing it, down 1 over 1. And again, I need another bold line. Now let's try, I can't test 0, 0 here. It's on the line. Let's try 1, 0. If I put a 1 in for x and a 0 in for y, I get a false statement again. I get 0 less than equal negative 1, which means for this line I should be shading over here. Do you notice how if I'm shading this way for this and I'm shading this way for that, I have no common shading. This problem has no solution to it. Let's try number 4. Here's my inequality. My y-intercept's negative 3, and my slope is positive 2. So let's graph that first. And I need a dotted line. I made dotted. Let's test the point. 0, 0 is a good testing point. So if I put a 0 in here and a 0 in here, I get a true statement this time. 0 is greater than negative 3. So I would want to be shading left. So I'm not actually doing it, but you can see I'm kind of pretending here with my pen. I would be shading over here. Okay, let's go to my other inequality. 1 is the y-intercept. That's here. And my slope is a half, up 1 over 2. Do that a few times. Okay, let's graph that. Now let's try 0, 0 in this one. So if I plug a 0 here and a 0 here, I get 0 greater than equal 1. That's not true. 0 is not greater than equal 1. So I should be shading the opposite side of this line, which is shading up. Well, if I combine the shading here with the shading here, I'm going to get that. Any point up here would be a solution to this system. Like, for example, I'm going to pick one. Negative 5, 10 is up here somewhere. I'm going to try to draw a big dot. Okay, that's definitely part of the solution set. This ordered pair would make both these statements true. The next thing we need to know, how can we look at a graph and write the system? It should be pretty easy. So for this picture, do you notice how we have a horizontal line at negative 2 and we shade it above? Okay, so I'm thinking to myself, okay, this is y equals 2. That's the horizontal line. And I'm shading a negative 2, I meant to say. Y equals negative 2. And I'm shading above that. So this would have to be greater than or equal negative 2. So there's my first inequality. Here's my second one. Y-intercept 0, slope 1. So here's y-intercept 0, slope 1. Now, I can't pick 0, 0 as a test point. Let's pick 1, 0. Now, do you notice how my shading in this example problem, my shading is right of this diagonal. So if I plug 1, 0 in, it better give me a true statement. So if I put a 1 in here and a 0 in here, what statement would make that true? Well, that would be true. Okay? 0 less than 1. So that's the symbol I need to use here. Y is less than 1x. That's why they have that. Y is less than x. There's your system. We just wrote it. Okay? Let's do one more. This one, okay, you can see a boundary line clearly here. I'm trying to do it in blue. That would be x is equal to 3, but we're shading left of that, so I would want x less than equal 3, which you can see here. And then here's my second line and boundary. Y-intercept negative 1, b is negative 1. Slope, it looks like we're going up 2 and over 3, up 2 over 3. So y would be 2/3 x minus 1. Now I just need the proper symbol. I'm shading above this, and you notice it's a dotted line, so my symbol has to be a less than or a greater than. Let's see which one it is. If I plug in 0, 0, it's got to be a true statement. If I put 0 in here and a 0 in here, I get 0 and negative 1. 0 would definitely be greater than negative 1. That's why you have the greater symbol. There is the system. What I would like you to do is pause the video and you can try numbers 6 and 7. Okay, I'm back here. So this vertical line would be x equals 3. But I am shading left of that, so I would want x is less than 3. There's my first inequality. Now let's get the second one. I have a y-intercept of 2, and it looks like my slope is down 1 over 1. So my next inequality would be y and negative 1x plus 2. And when I plug in 0, 0, that's got to be true. So if I put a 0 in here and a 0 in here, I need a true statement. 0 would be less than 2. Okay, so there's my system. Oops, I just erased that. Don't want to do that. Okay, so x less than 3 and y less than negative 1x plus 2 would be my system here. Let's go to this one. My y-intercept is 1, and my slope is down 1 over 2. Okay, so I would have y and negative half x plus 1. Now I need the right symbol here. I'm shading above this line, so 0, 0 has to be false. So if I plug a 0 in here and a 0 in here, I'd get 0 and 1. 0 greater than equal 1 would be false, so there would be that inequality. Now for the second one, negative 3 is my intercept for y, and my slope looks like it's up 2 over 1. Okay, so I have y and 2x minus 3. Now I just need the right symbol here. It's either a greater than equal, less than equal. Do you notice the bold line? When you plug in 0, 0, it has to be incorrect because I'm shading over here in my picture. So if I put a 0 in here and a 0 in here, I get 0 and I get negative 3. 0 less than equal negative 3 would be incorrect. That's what I want. So there's my system. To finish up, we can use graphing systems to solve a real-life problem. So let's look at this question. You have at most 8 hours to spend at the mall and at the beach. So x is the time at the mall, y is the time at the beach. So x plus y has to be less than or equal to 8. I have at most 8 hours to spend. You want to spend at least 2 hours at the mall. So x has to be greater than equal to. You want to spend more than 4 hours at the beach, so y has to be greater than 4. So you notice I just wrote a system of inequalities to describe this. They now want me to write and graph a system that represents the situation. I already got the writing down. It's here. Let's graph it. So let's do this inequality first. Y would be less than or equal to 8 minus x. So b is 8, and my slope is negative 1. So here's 8, and then down 1 over 1, and there's my bold line. Now, if I plug in 0, 0 for this statement, I need that to be true. So I'm mentally picturing that I'm shading below the diagonal. X greater than equal 2, that would be a bold vertical line at 2, and I want the values greater than that. Okay, and then finally, y greater than 4. Here's a dotted line at 4, and I want to be above that. Well, when I combine those shadings together, it's here. So any values in the shaded region or on these bold lines would be correct. So now, how much time can I spend at each location? For example, I could do 3 hours at the mall and 5 at the beach because it's right on that bold line. Or the book says I could do 2.5 hours at the mall, and what about 4.5 hours, for example, at the beach? That would be part of the shaded region. Okay. So these problems have infinitely many correct answers, which this does. That's why we have to graph these. I'm going to pause the video here. If you have questions, ask in class.